I would like to go back to the converging sequences. Now, I start with a metric space. So I have a topology, the topology that derives from the open balls. I know that this topology is a Hausdorff topological space. I would like to take a sequence of elements of X. What is the definition of convergence? Well, we say, based on what we said last week, that Xn converges to a limit L if, for any neighborhood of L, there exists a rank n, after which Xn is in this neighborhood. But we know that for this topology of the open balls, any neighborhood will be basically based on these open balls. So I can rewrite this equation here, this statement, as this statement for all positive epsilon, or actually non-negative epsilon, there exists a rank such that after this rank, Xn is in this neighborhood, which is the open ball around L of radius epsilon. So this is the definition that derives from the definition of the convergence of Xn in a topological space. But because I'm in a metric space in this specific topology, I can write this statement this way. Now, based on the definition of an open ball, I can replace this with this. I can basically write that it is equivalent to, for all non-negative epsilon, there exists a rank capital N, such that after this rank capital N, the distance between Xn and the limit is smaller than epsilon. Now, if you took calculus, I believe that you are familiar with this. And this is the definition that is given in a metric space. So as you can see, the definition of the convergence in a metric space derives from a more general definition in a topological space. You can see that it is a Hausdorff space because the topology derives from a metric space. So the limit L, there will be only one. Remember last week I said, I have some bad news for you. Sometimes the sequence converges to two different limits. Now, this week it's wonderful because you have a Hausdorff space, so this is not going to happen. You have only one possible limit, which is really a very good news. I'm going to give you an example. Let's do 1 over n squared. So that's a sequence. I would like to verify that it converges to 0. And if you do calculus, this is going to be simple for you. I start with a positive, or actually a non-negative epsilon. So epsilon cannot be 0. It's positive, but cannot be 0. So I start with non-negative epsilon. And what I want at the end is the distance between Xn and the limit, 0, to be smaller than epsilon. This is what I want at the end. So what I need to find is a rank capital N, after which this is true. So let's do it. To do it, I'm going to just go back from the very bottom here. So I want Xn, the distance between Xn and 0, smaller than epsilon. So what I need is, well, 1 over n squared to be smaller than epsilon. But to have 1 over n squared smaller than epsilon, I need to have n greater than 1 over the square root of epsilon. In other words, I need to find a capital N such that after this rank capital N, then small n is greater than 1 over the square root of epsilon. The square root can be written epsilon raised to power 1/2. Now it's easy. All I need to do is to choose this capital N. Let's choose capital N equal to the integer value of 1 over epsilon raised to power 1/2. In other words, 1 over the square root of epsilon. I take the integer part. In other words, what I do is choose a number n, which is an integer, which is going to be the integer part of 1 over square root of epsilon. If I choose this n, then everything is going to work. And now I can just look at my proof going from the top to the bottom, and it just proves that 1 over n squared converges to 0. Let us now define what is a Cauchy sequence. A Cauchy sequence is a sequence that verifies this statement. For all non-negative epsilon, there exists a rank n, after which for m and n greater than this rank capital N, the distance between um and un is smaller than epsilon. What it means is that the distance between two terms of the sequence is bounded by any epsilon I want, provided I go far enough in terms of rank. And if we have this, we have what is called a Cauchy sequence. And now a metric space that is complete, that is defined by a space where all the Cauchy sequences of elements of X converge. So if all of your Cauchy sequences converge, your metric space X is called complete. If some Cauchy sequences do not converge, or actually do not converge in the space X, then you have a space which is not complete. R is complete, the real line, that's complete. Q, which is all the fractions, P over Q, is not complete. As a matter of fact, R can be defined as a way to complete Q. Let me give you an example. Let's go back to xn equals 1 over n squared. We're going to prove that xn is a Cauchy sequence. Let's start with an epsilon strictly positive. What I want is to find a capital N such that after this capital N, the distance between two elements of the sequence will be smaller than epsilon. Let's choose n equals the integer part of 2 over epsilon plus 1, which can also have the notation with these brackets, upper brackets. So integer part of 2 over epsilon plus 1, in this case, q greater than p greater than n will provide 1 over p to be smaller than epsilon over 2. And to the question, why did I choose this capital N? The answer is because I wanted 1 over p to be smaller than epsilon over 2. And the reason why I wanted 1 over p to be smaller than epsilon over 2 is because this way, 1 over q minus 1 over p times 1 over q plus 1 over p is smaller than 2 times epsilon over 2, which means that 1 over q squared minus 1 over p squared is smaller than epsilon. So you see what we have? We have the distance between xp and xq smaller than epsilon. So what I did is to prove that for all epsilon positive, there exists a rank capital N, after which the distance between two elements of my sequence will be bounded by epsilon. Xn is a Cauchy sequence. Let me give you another example here. Xn equals the integer part of 10 raised to power n times square root of 2 divided by 10 raised to power n. Well, let's just compute it. X0, that's 10 raised to power 0, that's basically 1, times square root of 2. Square root of 2 is like 1.414, etc. So if I choose the integer part of square root of 2, that's 1, which I divide by 10 raised to power 0, so that I divide it by 1. So x0 is 1. x1 is 10 times the square root of 2. I take the integer part, and I divide by 10. So what I really get is like the first digits every time. So x1 is the first digit of the square root of 2. x2 is like 2 digits, so 1.41. x3 is 3 digits, and so on and so forth. Now, you can verify that xn is a Cauchy sequence. The distance between xp and xq, or xm and xn, is going to be bounded by any epsilon, provided you go far enough in the rank. But the Cauchy sequence will converge to square root of 2. Now, starting with the Greeks knew that square root of 2 could not be written as a number, an integer, divided by another integer. They knew that. It was like terrible for them. I mean, they really hated that. They had a problem with it. I mean, it's a good thing they're not Greek in the ancient times because it's really, really, really bad. But they knew that it could not be written a number, an integer of another integer. It's still true today, and that means that square root of 2 is not a fractional number, it's not a rational number, it's not in Q. So you can see that xn, though, every element of xn is an element of Q, is an element of these fractions. It can be written as a number divided by another number. Obviously, it's what's written here as a definition of xn. It's an element of Q, but it does not converge to an element of Q. So here you can see that you have an example of a Cauchy sequence which is not convergent in Q, which shows that Q is not complete.